All right, so in our last unit, which was essentially our first two tests, we did a lot of lessons on motion, right? Acceleration, velocity, distance. And the reason that things move in certain directions is because of forces. So that's what our next unit's all about. So our next two tests. And what a force is all about, it's a force is defined as a push or a pull. All right, so either way, you're trying to make something either move or move differently. All right, and again, the units are newtons, named after Sir Isaac Newton. And what a newton is defined as is 1 newton is the force required to accelerate 1 kilogram of mass at a rate of 1 meters per second squared. So what you see with the forces newtons is that here's the standard units that we have to stay in. You have to have your mass in kilograms, you have to have your distance in meters, and you have to have your time in seconds. All right, so that's key when we're dealing with forces. And then when we start mixing in motion. Now what we're going to be drawing to do these questions are what's called free body diagrams, FBDs. All right, now free body diagrams, which I'm going to show you here, are used to show the relative magnitude and direction of all the forces acting on an object at a particular point in time. All right, so it's just a picture, it's a diagram of all the forces acting on an object and labeling it, which helps us sort out different questions that we're going to be doing in reference to forces. All right, so for example, I want to draw a free body diagram of a wagon being pulled along a sidewalk. So here we're going to look at a few of the forces. Now here's the best part for me, because I am absolutely terrible with art, is that I draw every object when I'm drawing a free body diagram as a block. So that's really easy. Now usually I put in the weight of an object, or the mass of an object in the middle here, but I don't know the wagon. I should have maybe said it's 10 kilograms or something, but so there's our kilograms. There's our wagon anyways. Now, if I'm drawing a free body diagram of a wagon being pulled along a sidewalk, that means there is a force applied to the wagon. So I'm going to say that this force is applying it to the right. So I draw a little arrow here, and every force has, you got to basically name forces. Some of them you're making up your own names to sort things out, but other times forces just have names. And anytime there's a force that's pushing or pulling an object, I call it F of A, and that would stand for my applied force. There we go. All right, now, the other thing with forces is that when you have an applied force and it's being pulled along a sidewalk here, which means there's a surface in contact with our wagon, you have an opposition force to your applied force, always, unless stated, and that is our force of friction, which is, of course, some of these title or notation is not too crazy here, F of F, where the big F stands for force and the little F stands for friction. So again, that would be our force of friction. And the key here with the force of friction is it's always in the opposite direction of F of A. All right, so it's always in the opposite direction. If F of A is to the right, F of F is to the left. Now, here's another force that always, this is kind of like our invisible force, is acting on the wagon downwards. We have F of G, little g. Now, this is a standard name force because it's a standard force that we all experience, and that is the force of gravity. The trouble with some of these forces is they're invisible. Force of friction is invisible. Force of gravity is invisible. Your applied force, well, you can see a rope being pulled. Now, here's a secret other force. Again, we're going through some of these forces. Is that your wagon does not go flying into the ground because of the force of gravity. It is stabilized. And what happens is the ground pushes up on the wagon, believe it or not. And that force is called Fn. Now, the Fn is what's called our normal force. And it is always a force perpendicular, which means at a right angle, to the surface that the object is on. So perpendicular means a 90-degree angle. All right, so that's our normal force. Here's the blue line, that's our ground. And so perpendicular to the ground is our normal force. See, perpendicular to the ground right here. And then again, it opposes gravity. All right, so there's a free body diagram. There again is 4 very standard forces. You have an applied force that's making the wagon move, the force of friction that's opposing that motion. That's what friction does. It doesn't work with you. Force of gravity, always around because you're on Earth. And the normal force, which again is if the wagon's pushing down on the ground pushes back up on the wagon. All right, now let's see here. Draw a free body diagram of a rock sliding down a ramp. All right, so again, I'm going to draw the situation first, and then I will draw a free body diagram. So here's our situation. We got some kind of a ramp. Here's our ball. All right, now it's sliding down the ramp. I don't know how to draw that. All right, so I want to draw a free body diagram of that. Again, here's my ball. All right, so sorry, not my ball, my rock. Okay, all right, now it is sliding down the ramp. Now, the reason that our rock is sliding down the ramp is nothing's touching it, right? What happens is we have gravity. That's acting on the rock. It's making it go down. So there's our Fg, force of gravity. Now, as the rock slides down the slope, its motion is being opposed by friction. Notice how that I'm going to draw on my diagram I'm trying to roughly approximate the angle. All right, so our friction is going up as such. So it is opposing the motion. So gravity is pulling this rock, down, and the force of friction is opposing it because the rock is moving in that red line motion. And again, friction works in the exact opposite direction. All right, so if it's on an angle, friction's on an angle in the opposite direction. Now, the other force we have, again, we don't have an applied force, right? The applied force is friction, is that we have the normal force. This rock is pushing down on the slope. The slope is pushing up on the rock, again, at a right angle to the slope. So there is our normal force. And so again, on my free body diagram here, I'm going to draw the arrow appropriately, appropriate angle. And there is a free body diagram of our rock. The force of gravity is making it come down the slope. The force of friction is opposing that. And of course, we have the normal force, which is always there, of the ramp pushing up on the rock because the rock is pushing down the ramp. All right, what else we got here? Okay, so now, if all the force arrows, which are vectors, because they have magnitude, size, and direction, as I've mentioned, direction matters, are added together, the result is what we call F net. So F net is the net force of all the objects. Another thing is it's also called, well, how's my writing here? Called FR, which is, and we've had this before with our motion, the resultant force. So again, there's a couple of names, the net force or the resultant force. You can look at it either way. They're the same thing. And so this is kind of a familiar territory as we get to example 1, is that a car uses a force of 2,000 newtons east to move, and of course experiences a force of friction, which has to be in the opposite direction, of 180 newtons west, and also a wind resistance of 20 newtons west. find F of net. All right, so what I would do here is I have three forces. I have this one here, F1, I would call it. Here's F2. All right, and finally, F3. All right, and so if I am trying to find F of net, it's going to equal my F1. Oops, try to go big letters here. F1 plus F2 plus F3. So if I add up those forces, they will give me my resultant force, or in this case, what I would call my net force, same thing. Now, again, just like we dealt with velocity and displacement, directions here, we have straight line motion. So I'm going to, again, as always, make east positive, west negative. And so when I add these up, F1, I'm going to put positive 2,000 because it's in the east. F2, though, is west, so I'm going to have minus 180. 20 newtons is also west, so I go minus 20. And so now when I do a little bit of math here, my F net, again, it is a vector because it has a magnitude and direction here. 2,000 minus 180 minus 20, I believe I get 1,800 newtons. And because it's a positive force or positive number, I know the direction is east. All right, so again, just adding up vectors, same thing we've done before, but yet just a different scenario. Same process though. All right, so let's see what else we got here. If an object has the following forces acting on it, F1, F2, F3, F4, find F net. Same idea here. This time we have, up, down, right, and left. Whoa, okay. So let's see here. Now, if I'm finding F net, we just don't have a straight line here, but if I add F1 and F2 together, you can see that I have 50 newtons up and 50 newtons down. And so they essentially, when I add them together, cancel each other out. It's like taking one step forward and one step back. In this case, 50 newtons up, 50 newtons down. You're back to square one. And so when I add my vectors together, so I'm going to again have F1 plus F2 plus F3 plus F4. Again, when I'm finding my net force, F1 and F2 are, well, we have a 0 total. But again, with F3 and F4, we have 100 newtons right and 80 newtons left. Again, I always say right is positive, left is negative, just like graphing. So I have a positive 100 minus an 80. All right, and so in this case, I can figure out that, well, F net, again, magnitude and direction, I have 100 minus 80 is 20. And again, in this case, I said positive was right. So our net force is 20 newtons to the right. And that is our net force. Now, this is an example of two-dimensional motion where we have up, down, left, and right. But again, F1 and F2 cancel each other out. What would happen if that didn't happen? Well, take grade 12 physics and you will find out. All right, so that is just the beginning here of getting us into forces. All right, so again, some of the same